Hi there, everybody. Welcome to our next lesson for dynamics. This time we're going to be talking about something called Hooke's law. So this is all about the idea of spring forces or elastic forces. So an elastic force, also known as a spring force, is a force that arises anytime we change the shape of an object. So we say that it's a force produced by a distortion. So if we physically change the shape of something and it wants to bounce back the way it was, then we would say that's caused by an elastic force or a spring force. So, oh, sorry. All good?
My water bottle. I think I left it in here. Yes, I did.
Are you going to the park?
Me, yeah.
Nice. It is such a nice day for it.
What's that now?
Such a nice day for it.
Yeah, that's great. I will see you on Monday.
Yeah, man. Have a good one.
You too. Oh, these chairs look great.
It is surprisingly good.
Are these, is this grade 8 or grade 11?
No, these are grade 11s.
I like the one with the beer cozy.
I should show you what the grade 10s did though too. Their little mechanisms, their cardboard mechanisms
Oh, yeah.
are actually like super cool. Like I'm way impressed. They're all like tucked away in the thing, but I'll get on Tuesday. I'll get there to take some out.
That's a big lounger there.
Yeah, and the lounger is apparently I can lie in it, although I don't know if I feel comfortable doing it. We'll see.
It's just on test day.
Yeah. Yeah.
All right.
Yeah, man. Have a good one. Okay. So we can think of some examples of objects that might behave this way, and the most obvious example might be a spring, because, you know, spring forces. That's how they work. You stretch out a spring, it wants to go back to its original shape. You compress a spring, it wants to go back to its original shape. We call that original shape its equilibrium position. Or its equilibrium shape, and it's trying to return to that. So in addition to springs, well, we've got things like elastic bands or maybe bungee cords, right? As they stretch out, they want to snap back. And maybe there's some less obvious things like a bow, as in like a bow and arrow. When you pull back, when you draw the arrow back, it changes the shape of the bow and the bow wants to snap forwards. Or maybe even less obvious would be something like a basketball. Right? When the basketball hits the ground, the reason it bounces up is because the ground distorts the shape of the ball, and the ball doesn't want to be distorted. It wants to go back to being spherical. So it produces an upwards force every time it bounces. So anytime something changes its shape and as a result has like a restoring force that goes backwards, this is gonna fall under elastic force. Now Hooke's law is gonna follow. It's a bit of an idealized law where it's gonna work for objects that go back to the original shape. So you can imagine you stretch an elastic band, you let it go, and it snaps back to its original shape. Great. Of course, if you keep on stretching an elastic band, eventually it will snap and break, and that would be sort of in violation of Hooke's law, or basically just saying that we're going beyond the limits of Hooke's law. So for Hooke's law, the way this works is that the amount of force produced, the amount of force is proportional to the distortion. So what Hooke found was for sort of most regular everyday kind of objects, up to a point, if you distort them, then they're going to have a certain restoring force. And if you change their shape by double, you stretch the spring out twice as much, then it's going to have twice the force trying to return it to its original shape. So we can write this as an equation. And since it's a direct relationship, we could say Fe or Fs for spring, whatever you prefer, is equal to K times delta X. Now, I will point out that sometimes this is written with a little negative sign out front, and we'll kind of discuss why that is there. But I think sometimes we'll use it and sometimes we won't, just for simplicity's sake. So the first thing I notice is K. K is a value here, and I've given you the units newtons per meter, the number of newtons per meter. This is something called the spring constant. And for a given object, over a certain range, the spring constant is, big surprise, going to be constant. So what that means is, if you've got a bungee cord, it's going to take a certain amount of force to stretch it by a meter. And if you want to stretch it by 2 meters, you're going to need double that force. So it's just a linear constant, okay, measured in newtons per meter. And delta x, well, that's our distortion. Now, the fact that it's a delta, you can think of that as a change in position, or maybe as thinking of it as a change in shape or a change in the length. If we're talking about just a spring or an elastic, something that's linear, it's a change in length, and that works just fine. Now, back to this, this little sneaky negative sign here. Why might we write that? That's just a reminder that the distortion force, the spring force, I should say, is always going to work against the direction of distortion. So against distortion. So what do we mean by that? Well, if I have a spring and I stretch it, if I pull and apply a force this way to stretch the spring, then the spring force is going to work against that distortion and try and restore it this way. If I compress a spring by pushing on it with a force this way, the spring force is going to try to resist that and push back the other way. So my elastic force is always going to work against the direction of the distortion of the object. Okay, a couple quick examples here just to kind of put the math to work, and then we're on our way. So a student stretches an elastic band with a spring constant of 50 newtons per meter by 15 centimeters. So again, what we mean here is I've got like an elastic band, which is great because that's right in my artistic wheelhouse. And I'm going to take that elastic band and I'm going to stretch it out so now it's this long. Look at that. It's like we're really there. Okay. Now, the point I want to make here by drawing this out and subjecting you to that is the distortion is this amount here. This is my delta x. Delta x here is 15 centimeters. I don't know anything about the length of the elastic band, and I guess I don't need to solve this problem. The distortion is not how long it is, it's how much its length changed by. And of course, like we always will, we're always going to use base units for our calculations. So I got to make sure that's in meters. If I want to find the force, well, I know that the elastic force is equal to K delta X. So K in this case is 50 newtons per meter, and I stretch it by 0.15 meters. So that's going to end up being an elastic force of about 7.5 newtons. Now you notice here that I didn't use the negative sign. If you wanted to put a negative in here, that's fine. I didn't bother because it's just really saying how much force. The direction is going to depend on the situation, and I don't really know which way we're stretching it, so I don't really have enough information to tell you which way the force is acting. So I'm just going to leave it as an absolute value. All right, here's a bit of a throwback. Al McInnes, for those of you that can think back that long, used to use a wooden stick to play hockey, obviously, and with a spring constant of 850 newtons per meter. So when he took a slap shot, and I recommend take a look go find some slow motion videos of hockey players taking slap shots. When you hit the ice right in front of the puck, it changes the shape of the stick. It distorts the stick so that the stick snaps back and literally slaps the puck towards the net. So each hockey stick you have is going to have a spring constant or like a flex value. And so suppose his stick had a flex value of 850 newtons per meter. So if the elastic force is equal to K delta X, how much does it change shape? Delta X would equal Fe over K. And so 525 newtons divided by 850 newtons per meter is going to give me right around 0.62 meters of distortion. Now, I'm not sure how accurate that is. I'd have to check the math on that. That sounds like the stick bent quite a bit, but with the numbers we were given, that's the result. All right, last but not least, a girl sits in a human... All right, well, last but not least, a girl sits in a human slingshot, which I can only assume is something you can find at an amusement park or on YouTube or something, and has a spring constant of 10.5 newtons per meter. The sling is stretched out by 45 meters. What is her initial reaction acceleration when released? So I'm going to make a few assumptions here. I'm going to assume that the slingshot slingshots her directly forward and that there isn't any air resistance or anything like that. So I'm going to find my elastic force, which would equal to K delta X. And so we got 10.5 times 45, which ends up being right around 472.5 newtons. So they stretch her back and then they fling her forward. And so what is her initial acceleration? Well, F net, I'm just going to assume that the net force on her is just the elastic force. I guess this would be a more complicated or interesting problem if we had forces in different directions like gravity or air resistance or that sort of thing. But I'm just going to go with this. And so this is going to equal mass times acceleration. And so her acceleration would just be the elastic force divided by the mass. So 472.5 divided by 65, which is going to give us right around 7.3 meters per second squared. Now, it's worth just thinking about, before we move on, why in italics here we had initial. So why is this only her initial acceleration? Well, if you get stretched back in a slingshot and they let you go, your initial acceleration right off the beginning is going to depend on the force caused by that whole distortion. As soon as that distortion decreases, as soon as the slingshot becomes less stretched out, then your force is going to decrease. So this is an interesting situation where we would have a variable force acting on her as she gets slingshotted forward. That might be a lesson to explore for another day though. Okay, that is it for elastic forces.